So remember that limit definition of a definite integral that said that the definite integral from a to b of a function is actually the limit as n goes to infinity of a Riemann sum, right? Which we write with summation notation or a giant sigma, aka an infinite series, right? If n's going to infinity. So we've been looking at series that kind of look like that, right? Like they don't have the same form as a Riemann sum, but they still are infinite sums, just like Riemann sums, right? If we let n goes to infinity, the number of subdivisions. So there's actually a connection between these. So we can actually use an integral to help us prove whether or not an infinite series is going to converge or diverge. And we can do that through something called the integral test. So the cool thing about this is that you can actually use it for both convergence and divergence. There are 3 conditions that have to be met though. So if your function, which is what is the sequence rule inside of an infinite series, has to be 3 things. The sequence rule has to be continuous, positive, and decreasing. So all 3 conditions have to be met. You have to show all 3 conditions being met in order to use this. And if all 3 of those are true, you can look at the infinite series, right, which has that sequence rule of a of n inside of it. And you can also consider the improper integral of the function a of x. Right, so we are going to let the sequence rule equal a function, right, for all integers n greater than or equal to 1. Notice as well that the lower bound of the infinite series is the same as the lower bound of the infinite integral, right? So the cool thing about these is that we can oftentimes evaluate the improper integral to determine whether or not the improper integral is converging or diverging. So if we take the improper integral, if either one of them diverges, so does the other. So if you can see that the improper integral diverges, aka there is no limit that exists there, right? You know the infinite series is also going to diverge. If it converges, right? If you take your improper integral and it comes to an actual number, you know that the infinite series is also going to converge. And we have this monstrous looking inequality down here. So this is called our lower bound. So the value of the improper integral is the lower bound between the actual value of the summation, right? The actual sum, right? Because remember, oftentimes for infinite series, we actually can't find what the series equals, right? There's only rare instances where we can do that, like a geometric series or a telescoping series. So the value of the improper integral is going to be less than or equal the actual sum of the infinite series, which is going to be less than or equal to the first term plus the value of the improper integral. So we can actually find a lower and upper bound for what the actual summation is equal to, even if we can't find what the exact value is, right? We can find the 2 values that it has to be in between. This also lets us know that r of n, which is our remainder, for the nth number of terms is going to be equal to the sum from k plus 1 to infinity of a of n, which is going to be less than or equal to the improper integral from n to infinity of a of x. We don't have to worry about that so much. That just kind of tells you the remainder, so like the amount of error, that we're not going to really worry about that too much. So let's look at how to use this in a couple of examples to kind of see how to apply it. So we're going to determine if these 2 infinite series converge or diverge. And if they converge, we're going to find the upper and lower bound. So we're going to find that like window that the sum is actually in between. So let's consider this function first. So we want to get in the habit of always doing the nth term test first. So the first thing we're always going to do is try the nth term test for divergence. Right, remember that says that we look at the limit as n goes to infinity of the sequence, the rule of sequence, right? So that's 1 over 3n plus 4. That limit is equal to 0, so the nth term test is inconclusive. It does not prove that it diverges, so we have to move on. So the second thing we're going to do for this one is we're going to, of course, try the integral test because that's what this whole video is about. So to do that, we need to prove the 3 conditions that are required to be true. Remember, that is continuous, positive, and decreasing. So if we look at a of x, And we're going to let a of x equal 1 over 3x plus 4, right? And that's going to be for x greater than or equal to 1 because our starting value for the series is at 1. So we're not going to consider the x values that are smaller than that. So the first thing we need to prove is that it is continuous, right? So this is a rational function. So it's only going to be not continuous at a vertical asymptote for the x values, right? So we know that this is going to be not continuous when x is negative 4/3, right? Because that would make the denominator equal to 0. So a of x is going to be continuous, right, for all x greater than or equal to 1, right? If we wanted to be really specific, right, it's not continuous, right, because there's a vertical asymptote at x equaling negative 4/3, but that's not in the domain, so we don't need to worry about that. Okay. Our second condition is that it has to be positive. So let's look at that inequality. Let's prove whether or not it is going to be positive. So if we set 1 over 3x plus 4 greater than 0, right? We're looking for x greater than or equal to 1. Right, if we solve that, we get 1 is greater than 0, right? That is a true statement. So we can say that a of x is in fact positive for all x greater than or equal to 1. Right, because if x is greater than or equal to 1, the denominator is going to be positive, and 1 over a positive number is always positive. Right, so we're good there. The third thing we need to prove is that it is decreasing. Right, so that means we actually need to take a little derivative here. Right, so we know that a of x, if I rewrite this, is 3x plus 4 to the negative first power, which means that my first derivative is going to be negative 1 times 3x plus 4 to the negative 2 power, right, times my derivative of the insides of 3. So that's going to equal negative 3 over 3x plus 4 all squared. So if we look at this, right, the denominator, 3x plus 4 squared, right, this part is always going to be positive because it's something squared in the bottom. Right, the only time when it's not positive is when it's 0, but it's only going to equal 0 at negative 4/3, where x equaling negative 4/3, and that's not in the domain, so we don't need to worry about it. And negative 3 is always going to be negative. So that means that a of x is decreasing, right, on its domain of x greater than or equal to 1, right? So this tells us, right, it's always going to be less than 0, right, for x greater than or equal to 1, right? Since the derivative is always negative, we know that it's decreasing. So now that we have gone through all three of those conditions, right, I am already out of room. Should have given myself a second slide. My bad, right? We're going to actually say, okay, right, let's consider the improper integral from 1 to infinity of our function 1 over 3x plus 4 dx, right? So we're going to be good mathematicians, so we're going to say, okay, that is equal to the limit as b goes to infinity of integral from 1 to b, right? Technically, I need to do a little bit of a u sub, but I'm going to just do this in my head. Sorry, so this is 1 over x essentially, so we know that this is going to be the natural log of the stuff inside, and I would need to counteract what the inside derivative is, so I'm going to multiply it by 1/3. Right, and then I'm evaluating from 1 to b, holding my limit notation there the whole time. So now if I take the limit as b goes to infinity, I get 1/3 of the natural log of 3b plus 4 minus 1/3 of the natural log of the absolute value of 3 plus 4, and that's 7. Okay, so as we let b go to infinity, right, 3b plus 4, this part is going to infinity. And as the natural log goes to infinity, right, the natural log is going to infinity as well. So our limit overall here is equal to infinity minus 1/3 natural log of 7. So this is equal to infinity, right? So in conclusion, right, so we can say since the integral from 1 to infinity of 1 over 3x plus 4 dx diverges, we can draw the conclusion by the integral test the infinite sum, right, from, oh, that was an awful sigma. Let's try that again. Sum from 1 to infinity of 1 over 3n plus 4, right, also diverges. Okay, let's look at a second example, right? So a lot of work for that integral test, but that's okay. Okay, so now let's look at this one. So, right, we'll start it off the same way, right? We're going to do the nth term test first. Right, always want to get in the habit of checking that first. Limit as n goes to infinity of 1 over n cubed, right? That equals 0. So inconclusive, so we don't know whether or not it's going to converge or diverge, so we're going to move on, right? So for the integral test, we're going to let our function a of x equal 1 over x cubed, right, for x greater than or equal to 1, since that is where our summation is starting. Right, so 3 conditions. Is it continuous? Yes. 1 over x cubed is only not continuous at x equaling 0, not in the domain. Right, so we can say a of x is continuous. Right, you don't necessarily need to go about showing all of the algebra and stuff for y. You just need to be certain that that is in fact true, because if one of these conditions isn't met, you can't use this test. You have to do something else. Right? Okay, is it positive? Well, x cubed is always positive when x is greater than or equal to 1, so 1 over a positive number is always going to be positive. So we can say, right, our function is positive for x greater than or equal to 1, right? And if we take a derivative, right, 1 over x cubed, the derivative of that is negative 3 over x to the 4th. Right? Negative 3 is always negative. X to the 4th is always positive. So this is always going to be less than 0 for x greater than or equal to 1. So we can say, since the derivative is always negative, right, this is also decreasing for all x greater than or equal to 1. Right? So now let's consider the improper integral from 1 to infinity of 1 over x cubed dx. Right, so I'm going to use my limit notation here. Right, so b goes to infinity of the integral from 1 to b of x to the negative 3 dx, just rewriting it for ease. Right, so that's going to be the limit as b goes to infinity. If we do our power rule, that's going to become x to the negative 2 over negative 2. From 1 to b, so that's going to be the limit as b goes to infinity. If I plug my upper and lower bound in, that's going to be negative 1 over 2b squared, and then it's going to end up being plus 1 over 2. So then the first part, as b goes to infinity, right, that's going to 0. So overall, my limit is equal to 1/2. So since 1/2 is a finite number, right, we're going to get that this converges. So we can say, as our conclusion, right, since the integral from 1 to infinity of 1 over x cubed dx converges, right, by the integral test, the infinite sum from n equaling 1 to infinity of 1 over n cubed also converges. Now, since it converges, we can, there we go, spell that right. So since it converges, we can actually find the lower and upper bound for the actual sum. So what does the actual sum of this infinite series have to be between? So for our upper and lower bounds, the lower bound is always the value of the definite integral, improper definite integral. That's always going to be less than or equal to the actual sum from n equaling 1 to infinity. And that's always going to be less than or equal to the first term, right? So a1 for this series is 1 over 1 cubed, which is 1, plus the value of the improper integral. So we can now just plug in our numbers. So we can say that 1/2 is less than or equal to the actual sum from 1 to infinity of 1 over n cubed, which is less than or equal to 1 plus 1/2, which is 3/2. So the actual value of this infinite series, right, this infinite summation, has to be somewhere between 1/2 and 3/2. So if you're looking at the integral test for convergence for infinite series, it might bring back memories of learning about improper integrals in those special improper integrals that we called p-series, right? And those are directly related to series because we also have p-series in infinite series. So a p-series is a series that's in the form of the sum from 1 to infinity of 1 over n raised to a power, right? So that's called a p-series, and p has to be a positive constant. So the p-value is the exponent, and it is a constant exponent. The exponent isn't changing as the series goes along. So one of these situations is a very special type of series that actually comes up a lot when we're examining infinite series, and it's called the harmonic series. And that's when p is equal to 1. So the series of 1 over n from 1 to infinity is the harmonic series, and it's super duper important. We're going to use it a ton, especially with the comparison tests. So with that, we get a special test for convergence and divergence called the p-series test, and it is specifically for series that are p-series, right? You can only use it for p-series, why it's called the p-series test, right? So there's 3 scenarios. If p is equal to 1, if you have the harmonic system series, the series automatically diverges all the time. If your exponent is between 0 and 1, right, the series is going to diverge, right? This should all feel very familiar to improper integrals in the p-series that we talked about then. The only time that a p-series is going to converge is if p is greater than 1. So like the sum of 1 over n squared from 1 to infinity, the sum of 1 over n to the 3.25 power, right? That's going to converge. But something like 1 over n to the 0.5 power or the 0.75 power, that's going to diverge every single time. So if you recognize it as a p-series and you remember the p-series test, you can automatically state whether it's going to converge or diverge.